Good morning, students. The topic of my lecture is transistor types and its current components. In the previous lecture, we discussed about the introduction to transistors, in which we discussed about the transistor, its terminals, the basic terminology, transistor, why it is termed a transistor, how many terminals we have a transistor. Like you can see, we have a three-terminal device, transistor three-terminal device. One is your, these are three scientists which invented these transistors, and the three terminals are the emitter, base, and collector. This we discussed in the last lecture, and we talked about the emitter, why emitter has a high concentration of dopants, base has a least amount of dopants, base is very thin, and size is also very small. In case of base, emitter has a moderate size, the number of dopants inside the emitter is high. We have the high majority carriers in case of your emitter, and collector junction has a large size, but the concentration of dopants is moderate. It's not that very high. We discussed about this in very detail, that why this is like this. We have why the collector size is large, why the emitter size is small, why the base is smallest. So that was all discussed in detail. Now we'll have just a big small glance and we'll switch on towards the transistor current component in today's lecture. So these were two types of transistors. Basically, we have the PNP and we have the NPN transistors. In case of PNP, we have the three terminals, emitter, base, and collector. And similarly, in case of NPN, also we have three terminals, emitter, base, and collector. And this is a symbolic representation of PNP and NPN transistors. The arrowhead is always associated with the emitter junction of transistor. Why? Because it depicts the conventional flow of current. And current always flow from the positive terminal towards the negative terminal. Types of transistor. There are two PN junctions. When they are joined together, when we join actually the two PN junctions, we actually comprise of two types of transistors are made, that is your PNP and your NPN. And this is the emitter junction is always associated with the flow of current. It is the highest concentration of the charged particles is there inside your emitter junction. Then we have the base. Base is associated with the transference of the charged particles from the emitter towards the collector side. So it is just associated with the transference of the charge carriers from the emitter towards the collector side, and collector has a large size. It has a large size, and the number of charge carriers are moderate, and only the current that is flown inside your collector junction is because of the major concentration of the electrons or the holes which are being transferred in majority from the emitter towards the collector. So this is the when we talk about the operation of transistors, this is what actually happens. This is the symbolic representation and a diagrammatic representations of your transistor configurations. This is your transistor which we have. This is your emitter. This is your NPN transistors, because basically because the flow of current is outward, that means it is from the positive towards the negative. So this is your P, this is your N, and this is again your N. So NPN transistors basically, and we are supplying a voltage of 10 volt. A 10 volt supply voltage given to it, and the 10 volt supply voltage, we have this concentration of electrons and the holes which are being generated in the NPN transistor. The emitter current flows from the emitter towards the base and from base towards the collector. This arrowhead is always the conventional flow of current. The arrowhead always depicts as the conventional flow of current. It is not associated with the actual flow of current, because as you can see over here also in this very diagram also, the emitter is shown outward. The flow of emitter current is outward, but in actuality it is from emitter to base and then from base to collector. So actual flow of current is opposite, but the conventional flow of current is always from positive towards the negative terminal. So it is termed as a conventional. It is not the actual that is being flown inside the body of the transistor. Then we have this junctions. What is the biasing level at various junctions of transistor? We have the this three junction. We have two junctions basically. One is your emitter based junction. One is your collector based junction. And for the emitter based junction, we have applied a voltage of 0.5 volt. Okay, a 0.5 volt is being applied to it. And for collector based junction, we applied the 10 volt of reverse bias voltage. Collector base is reverse biased and emitter base is forward biased. And when the emitter base is forward biased, what was actually happening? The emitter current, all the majority carriers which were present inside the emitter, they were being transferred from the emitter towards the base. Base being very thin and lightly doped, it just transfers all the charged particles which are moving from the emitter towards the base and only recombining with certain 5 to 10% of the charged particles, and that base, and they comprise to the base current, and that base current is actually grounded because it is not required to us for the circuitry elements. So that is being grounded, and rest 90 to 95% of charged particles are moved from the emitter towards the collector section. Okay, and hence we get the output voltage at the collector. Now, why this is reverse biased and why this is forward biased? Emitter base is always forward biased and collector base is always reverse biased in the active region for the active operation of the transistor. Now, why it is so? It is so because when the emitter base is forward biased, a large amount of charged particles can move away from the emitter base junction and they will move towards the collector, where they can be collected and they can be taken out. And when the collector base is reverse biased, that means the charging biasing level of the particles and the biasing level of the voltage which is being provided to them, they are opposite to each other, because in case of NPN transistor, the electrons are majority carriers, they have a negative charge over them, and potential that is being provided to them is your positive potential. So negative and positive get attracted towards each other. There will be strong attractive forces created at the collector junction, which will collect all the charged particles from the collector of the transistor. So in this way it is working, and in this way the transistor works from the emitter towards the collector junction. So this shows at how practically we are actually implementing this kind of implementation in case of your transistors. So this is how the emitter base is forward biased and the collector base is reverse biased. Okay, class. Now you can see it over here that we have already told you that we have transistors in which the major concentration of current is always being produced because of what? It is always produced because of the concentration of majority charge carriers which are flowing from, which are actually flowing from which section to which section? They are flowing from emitter towards the collector. So whenever the charge particles they flow from emitter towards collector, we get what? We get the maximum concentration of particles at the collector junction. So according to this junction or this definition, we can derive a formula for the emitter current. This IE is what? This IE is the amount of emitter current, and emitter current is always equal to what? It is a combination of collector plus base current. Why collector plus base current? Because emitter current is always associated from the point emitter towards the collector. It is just a transference of the charged particles from emitter towards the collector, and when these charged particles are actually moving, what happens is they are collected in the collector junction and they are transferred from the base. So a combination of collector plus base is always equal to the emitter current. So combination of collector and base is always equal to the emitter, because emitter, this collector junction or the collector terminal of the transistor and the base terminal of the transistor, they don't have any of their own value of current. The most of the component of current is being produced by what? By which terminal? It is always being produced by the emitter terminal. So the concentration of charged particles is always from the sum. We can see it is sum of your what? It is the sum of your collector plus your base current is always equal to what? It is equal to your emitter current. Okay. So according to this, we can derive the formula for this current value also, because the value of this base current is always grounded, because I've told you that base is always grounded, and only 5 to 10% of charge particles which are being produced in the base junction, they are replenished, or they are grounded so that they can be zero, because they can hinder the actual performance of our transistor otherwise, because base current is always found because of the recombination of holes and electrons, and that is not required in our case, because in case of transistors the flow of current is only because of the flow of the majority charge carriers. So we can say it over here that the alpha is what? This alpha is given by the ratio of IC by IE. It is a ratio of IC by IE, and it is given by alpha. And alpha is what? Alpha is the current amplification factor. Alpha is a current amplification factor. It means, what do you mean by current amplification factor? It means that it is actually the amount of current that is being amplified. The amount of current that is being amplified is known as a current amplification factor. Okay, so current amplification factor is given by alpha, and it is a ratio of your collector current to the emitter current. Amount of collector current that is being produced by the amount of emitter current that is being produced, that is IC by IE. So that in all gives you the value of alpha, or the current amplification factor. So alpha is a current amplification factor over here, and the value of alpha, because in case of numericals which we're going to solve, alpha lies always between 0.95 and 0.99. The value of alpha is always less than 1. It is always less than 1, and it lies normally between 0.95 and 0.99. It's the standard value of alpha. And then this is a major part now which we are going to study in this very junction. We have the conditions. These are the conditions. We have the forward bias, forward reverse, forward forward, reverse reverse, and reverse forward. Okay. Now first condition is forward reverse. Forward reverse means when the emitter base is forward biased and collector base junction is reverse biased. When the emitter base junction is forward biased and the collector base junction is reverse biased, then that is which condition? That is the active region. This is the active region operation which we are normally operating for a transistor. Transistors normally operate in the active region. For the basic operation of transistors, we make them operate in the active region, and for active region operation, we generally prefer to emitter base junction to be forward biased and collector base junction to be reverse biased. And when the emitter base junction is forward biased and collector base junction is reverse biased, then we can have the region of operation as, we can term that region of operation as active region. And active region is the most appropriate region of operation for the working of transistors. Okay, then the second is your second condition is forward forward. Forward forward means when the emitter base junction is forward biased and collector base junction is also forward biased. When both of the junctions, that is emitter base and collector base, both of the junctions are actually forward biased, then what will happen? Then the transistor will work in the saturation region. Then the working of transistor will be in the saturation region. Why saturation region? Why it is termed as saturation region now? It is termed as saturation region because when we talk about saturation, the whole circuit will act as a short circuit. There will be a huge amount of current will be produced because emitter base is also producing a huge amount of current because of forward bias junction. And similarly, the collector base is also forward biased, and it will also produce a huge amount of current, and the whole circuit will act as a short circuit, and a huge amount of current will flow in it, and it is very dangerous. It can hamper your device. It can get your device damaged. So normally transistor is not made to work in the saturation region. Reverse reverse. Reverse reverse means when the emitter base is reverse bias and collector base also is reverse biased. When both of these junctions are reverse biased, then what is the region of region of operation? The region of operation becomes cutoff. Cutoff means both of the junctions, emitter base and collector base, are working, they are biased in the reverse biased region. And in case of reverse biased region, do we flow any current? No, there is only a flow of current because of minority carriers. And the concentration of minority carriers is very low in case of your this emitter base as well as of collector base. The concentration of charge carrier is very, very low, which makes the circuit to work in the cutoff region. Cutoff region means it will act as circuit will act as your open circuit. There will be a very small amount of current that is be flowing inside it, and that is known as a dark current or the reverse saturation current. But the concentration of that charge, this current, because of minority carriers or because of reverse bias junctions, will be very, very less, and it is termed as your dark current or the minority charge carriers. In terms of current, it is in microamperes. It is very less, and transistor doesn't work in this cutoff region. The fourth region is your reverse forward condition. Reverse and forward condition. In case of reverse and forward condition, what is actually happening is we are getting a condition for emitter base, we have the reverse bias, and for collector base, we have the forward bias. When the emitter base is reverse biased and the collector base is forward biased, what is the region of operation? It is in the inverted mode. Inverted mode, or it will act as an inverter. Inverted mode. Why it is termed as inverted mode? Because the junctions which was to be made into the forward biased, it is being reverse biased, and junctions which were made to be reverse biased, they are made to a forward biased. So emitter base was reverse biased and collector base was forward biased, and reversing or the just the exchanging of these regions of the operation will make it work as an inverter. It will be working as inverter. Okay, so the transistor normally operate in the active region where the emitter base is forward biased and collector base is reverse biased. It can't work in the saturation region. It can't work in the cutoff region and inverted region. So this is the most appropriate region of operation for the transistor, that is your active region. Okay, class. So this was about the conditions of the transistors in which they work and about their regions of operation and their designations to which they are associated. That is reverse bias, forward bias, reverse forward, and forward reverse. So these were the basic conditions which were associated with it. Okay, class, you can see it over here. In this very topic, we'll be discussing about the various transistor current components. Transistor current components means what are the various transistor current components which are generated when we talk about the concentration of particles which are present inside the emitter, base, and collector, and how those charged particles are moving, and how those charged particles are getting affected by the bias to which we are providing to them, whether we are providing the forward bias or reverse bias or open circuit or short circuit, whatever the bias condition is there, what is the effect of that bias condition on the particle concentration and the movement, or the generation of collector current or generation of the current at the output junction. So let's start with it. This is your basic transistor. Now we have taken the transistor as PNP in this case. We are talking about the PNP transistor in this case. In case of your PNP transistor, the maximum majority carriers in case of emitter are the holes. The majority carriers in case of your emitter are holes because it's a p-type material in case of your emitter, and collector is also p-type. It is also having concentration of holes as a majority carriers, and electrons are there, but electrons are only in the minority carriers. Okay, so first of all, the current that is being generated inside this transistor is because of this hole concentration, or because of this holes majority carriers, because it is forward biased. It is forward biased. P type is connected to the forward terminal or the positive terminal of the battery. So this is the VEB, means the voltage across the emitter base junction. Voltage across the emitter base junction is always forward biased. Okay, so For the active region operation, we discussed in the previous slide. For the active region operation, the emitter based junction is always forward biased and collector based junction is always reverse biased. And the transistor works with the best efficiency in case of your active region. So for this active region, emitter base is made forward biased over here. And when this emitter base is made forward biased, what actually happens is the majority charge carriers which are there present inside the emitter junction are what? They are the holes. So we have written over here is IHE. Your H small h reads the concentration of the holes. The I stands for current. So the generation of current because of the majority carriers, which are the holes. So which are holes is denoted by H, and E, capital E stands over here for the emitter junction. So for the emitter junction, we have the carrier concentration of holes in majority, and the current that is being produced is known as I. Okay. Now this IHE, which is being produced over here in majority charge carriers, is being transferred because of this forward bias voltage. A strong repulsive force is created over here, positive potential provided from the battery, and the positive charge of the holes. They get a strong repulsive forces, and hence what happens is the charge particles or the majority charge carriers, they start moving from this part, from this junction towards the base side. They start moving from the emitter towards the base side. Now when they move towards the base, what happens is this is a junction of emitter junction. This is your junction of capacitance, collector, sorry. Collector junction is your emitter junction. So this they start what? They start leaving the emitter junction and they start moving towards the base junction now. Now, when they start moving towards the base junction, what happens is 90 to 95% of the charged particles, they are transferred from this emitter towards the collector, and rest 5 to 10% are what? They are recombined with the particles, majority particles which are present inside this N-type region. Now, this base is N-type. Now, base is N-type. This is very thin. This is lightly doped and very small in size. So all of these three factors are making the base least conductive for the current. This is only used for transference of particles, majority particles, or the transference of electron current or the whole current which is being produced inside this emitter junction towards the collector junction. So when these particles are being transferred from emitter towards the collector, certain 5 to 10% particles from this holes, they will recombine with the electrons which are in majority in this N-type region, and they will comprise a base current. They will comprise a base current, and that base current is known as grounded. It is known as a grounded current also. It is grounded, it is earthed. So its value becomes 0. And base current is always equal to what? It is the particles which are subtracted, that is IHE minus IHC. The particles which were being transferred from this emitter junction and the particles which were reaching towards the collector junction. If we subtract both of these particles, the amount which we get is your base current. IHE minus IHC. The particles which are not reached towards this collector junction is your base current, and it is always grounded. Now the particles after recombination with the base, that is 5 to 10%, 90 to 95% of the particles which are being transferred from the emitter towards the collector, they comprise to the collector junction and they form the which particle current over there, because base is also p-type material. So they will comprise the IHC value over here. IHC means I stands for current, H stands for holes, and C stands for collector. C stands for what? C stands for collector. So here the particles, they will recombine in this region and they will form the collector current over here. That is IHC. I current, H for holes, and C for the collector. Now this is for the forward biased value. Okay. Now there are certain particles which are in the minority also. There are minority charge particles also. So minority charge particles in case of your emitter are electrons. In case of your emitter are electrons. So total amount of current that is present inside this emitter is what? It is IHE plus IEE. IHE plus IEE. H stands for holes, E stands for emitter, E stands for electrons, E stands for capital E stands for emitter. This is the total concentration of the particles which is comprising this emitter current. Okay, so what happens over here is this is in the minority part. These particles are in the minority charge particles. So when they reach towards the collector, this is the concentration of the current that is being produced because of the forward bias voltage. Okay, now collector base is what? Collector base is reverse biased. Collector base is reverse biased, isn't it? So when this collector base is reverse biased, what happens is the amount of charge particles which are reaching over here, this is at the positive charge, isn't it? This is at the positive charge, and the particles and the battery or the potential which you're providing to them is the negative potential. So positive charge and negative potential, they make what? They make the reverse combination. So the strong attractive forces are coming across it, and they will be what? They will be attracted to it, strong attractive forces, and they will be ejected out of this collector junction. Okay, but because of this reverse bias, now there will be some amount of that reverse bias current also. Yes or not? Because of this reverse bias voltage, yes, it will be. It will be there, and that is known as your reverse saturation current, which is being produced because of this reverse bias voltage. And reverse saturation current is produced because of what? It is produced because of the flow of minority carriers. And minority carriers are what in case of your p-type material of collector? They are the electrons. They are the electrons. So they form the amount of minority in case of your minority carriers, or dark current is being produced because of the flow of minority carriers. Now, what is the concentration of these minority carriers that we'll be studying right now? This is the amount of flow of minority carriers which are moving from this emitter towards the collector. So this is the concentration of the minority carriers. And when this reverse bias voltage applied to them, it gets attracted to it and it will start moving toward this section. So one concentration of minority charge carrier is IECO. And this ISCO is the current that is a minority in case of your base. This is in case of your base, because base is N-type material. N-type material means holes are in minority in case of your transistors of base type. So this ISCO plus IECO, which was a minority in case of your IEC, was in minority because in case of your emitter and collector, and IHCO is in minority in case of your base. So the combination of this IHCO and IECO, they will form what? This combination of IHCO plus IECO. Why this CO term is attached to this? O terms means over here is a reverse saturation current. This is a reverse saturation current that is associated with the collector terminal. So this O denotes over here the reverse saturation current. So this is termed as your ICO. Collectively it is known as your ICO. The collection of IHCO plus IECO. So this is the IHCO plus IECO. They will comprise what? They will comprise a total reverse saturation current, that is your ICO. They will comprise a total saturation current, that is your ICO. IHCO, IECO is equal to what? It is equal to ICO. ICO is a total reverse saturation current that is being produced in this collector junction. Okay, this is the total concentration of the current components which is being produced inside your this transistors. Okay, so this is one part of transistor. Next part of this is what are the two cases which we come across when we talk about this case 1 and case 2. What are two cases which when we come across them? Two cases are, the first case is when the emitter is open circuit. when the emitter is open circuit. When the emitter is open circuit, what happens is then the concentration of the emitter current will be equal to 0, because when emitter is open means there is no supply voltage given to the emitter junction. When no supply voltage given to emitter junction, what will happen? Will there be any flow of current in the emitter? No, there will be no flow of current. So there, in this case, the amount of emitter current will be equal to 0. And if this value is 0, that means IHC, this will also be equal to 0, because if this is 0, this will also be equal to 0. Then what will the concentration of current when the emitter is open? When a emitter is open, only the reverse saturation current, that is this value, this ICO will only flow in it. Only ICO will flow when there is a when emitter is open. When the emitter is open, only ICO current will flow inside this emitter junction. This is the first case. Now, when the emitter is short, when the emitter is closed, that means when we are supplying the amount of voltage to the emitter, then what will happen? The amount of current inside this collector, this output junction IC, will be equal to what? It will be equal to IHC plus ICU. IHC plus ICU. This IHC is the amount of current that is being transferred from the emitter towards the collector junction. Amount of current that is being produced from the emitter towards the collector junction, and will comprise the IHC value of current. That is the amount of majority carriers which are present inside this, that is IHC, and ICO is the reverse saturation current that is being produced inside this collector junction because of this reverse bias voltage. So this is the two cases which we come across when we talk about the concentration of the charged particles, about their values, and about their concentration, the forward and the reverse biased junction. So in the active region operation, when the emitter junction is forward biased, the collector junction is reverse biased, the amount of collector current, when the collector current, amount of collector current is always equal to what? That is equal to IC into alpha IB plus what? Alpha IB plus ICU. So this is the actual equation of the, this is the actual equation of what? The actual equation of the value of collector current which we get, actual value of current collector current which we get when the transistor is operating in the active region. When the transistor is operating in the active region, this is the amount of current, collector current which we are getting inside the transistor. This IC is a collector current, it is equal to alpha I. Alpha means the current amplification factor alpha. IE is the emitter current, and ICO is the reverse saturation current that is being produced inside it. ICO is a reverse saturation current that is being produced inside this circuit. So in this region, because transistors are actually operating in the active region only, so this constitutes towards the total current of the circuit. So this was all about your transistor current components and their values, which we are getting by the various biasing conditions and various region of operations which we are providing to them. According using all these values, we can actually calculate the amount of current that is being produced inside this transistor using the concentration of charged particles as a holes or as a electrons. So that is what we are actually required to note in this very case.